So Zeke Hausfather is here with us. He is, forgive me for reading, the climate research lead for STRIPE, an internationally renowned climate scientist whose research focuses on observational temperature records, climate models, carbon removal and mitigation technologies. He also works as a research scientist with Berkeley Earth and as a science contributor to Carbon Brief. He was formerly the director of climate and energy at the Breakthrough Institute, senior climate analyst at Project Drawdown, the lead data scientist at SS, chief scientist at C3AI, and the co-founder and chief scientist of Efficiency 2.0. He has master's degrees in environmental science from Yale University and Vrije University, Amsterdam, and a PhD in climate science from the University of California, Berkeley. Zeke, thanks so much for joining us, and we look forward to your talk. Thank you.
See if I can switch the PowerPoints. There we go. Okay, so thank you everyone, and thank you for having me here. I have not given this talk before, so bear with me as we do it together. So I wanted to talk about climate hope because what I see out there right now, particularly among young people, is a lot of climate despair. 10 years ago, when I first got into this field and started doing climate science, we spent all of our time arguing with the skeptics, the people who said, oh, it's the sun causing climate change, oh, the records are biased, the data's adjusted. Nowadays, when I'm talking about climate change with people, the first question I always get is, oh, it's too late, we're all doomed, right? Or we're screwed, there's no way to solve the problem. And I think that's a really problematic framing because it's disempowering. It tells people that they can't do anything about it, that it's too late, and that it's wrong. And it glosses over a real amount of progress the world has made, particularly over the last decade. And so I think what we really need to embrace is a cautious climate hope, not a blind optimism that says we're in the best of all worlds and things are going to be fine, but also not a pessimism that says, you know, we're disempowered, we can't actually do anything. Because if we want to solve thorny problems for society like climate change, we need to do a lot of things. And to do a lot of things, we need to realize that we have the agency and we have the power to do it. So I want to talk about hope. Another thing that I always remember is Stephen Schneider, who's sort of one of the founders of modern climate science, famously said that when it comes to climate change, the end of the world and good for us are the two least likely outcomes, even though often our debates revolve between the two. And so, you know, we can both acknowledge that we have made progress in avoiding the worst climate futures, but also that we still have a long way to go to get to the worlds that we want and that are going to be best for society. So we have to start out whenever we're talking about climate change by emphasizing that the world is not on track today.
Can I just leave
Of course. See if we can hide that really quick. That the world is not on track today to meet our climate goals. This is one of the more iconic charts from climate science. It's the global temperature record. Each blue dot is the temperature for the world as a whole. The red line is sort of a 10-year moving average. And this is a product that I produce with the Berkeley Earth Surface Temperature Initiative in Berkeley Earth. And here we see that, you know, global warming has really accelerated the last few decades. The world has warmed by about 1.2 degrees C since the pre-industrial period. And most of that warming, about a degree of it, has happened just since 1970. Now, if we continue warming at the rate that we have been over the last 50 years, we'd expect the world to pass 1.5 degrees in the early 2030s and 2 degrees in the late 2050s. And that's not a world we want to be. We want to bend that curve. And when people look at this, you know, they often get worried. They think, well, it's going to be really hard to change where we're going today. And we also tend to focus a lot on these specific thresholds, like 1.5 and 2 degrees, to the extent that, you know, people use slogans like 1.5 to stay alive. And there's this idea that if we pass these thresholds, it triggers some sort of process that, you know, leads to really bad outcomes for the planet. And as I'll discuss later in the talk, that's not necessarily the case. You know, certainly the more warming the world gets, the worse it is for all of us, the higher the impacts become. But the climate is ultimately a matter of degrees, not thresholds. And the more we can limit warming, the better. Every 10th of a degree matters. So I'm going to try to show a little video clip, and hopefully this will work. We had some audio issues earlier, but let's see if this will work.
Our home is burning. Rapid climate change is destabilizing our world. It seems our emissions will not fall quickly enough to avoid running. Our home is burning. Our home is burning. Rapid climate change is destabilizing our world. It seems our emissions will not fall quickly enough to avoid runaway warming, and we may soon hit tipping points that will lead to the collapse of ecosystems and our civilization. While scientists, activists, and much of the younger generation urge action, it appears most politicians are not committed to doing anything meaningful, while the fossil fuel industry still works actively against change. It seems humanity can't overcome its greed and obsession with short-term profit and personal gain to save itself. And so for many, the future looks grim and hopeless. Young people feel particularly anxious and depressed. Instead of looking ahead to a lifetime of opportunity, they wonder if they will even have a future or if they should bring kids into this world. It's an age of doom and hopelessness, and giving up seems the only sensible thing to do. But that's not true. You are not doomed. Humanity is not doomed.
So I think I might need to temporarily mute this while I do that. Okay. So this is a video that I helped a team called Kuehnast put together that's sort of telling the story of climate hope, of why we are not necessarily doomed. And I'll sort of weave it in with my talk today because I feel like it does a really good job of illustrating some of these points. And so this idea of the world is heading in a terrible direction, nothing is happening to turn it around, should we even consider bringing children into the planet given how bad it's going to become, is remarkably widespread, particularly among younger generations today. But it also is missing out on a big part of the story, which is things have really changed over the last decade. And to explain why, I'll start with another quick video clip and then go into some specific details.
Our hope. A decade ago, for lack of action and perspective, many scientists assumed a 4+ degree world was our future, and a lot of public communication focused on exactly this future path. Luckily, it's much less likely that this version of the apocalypse will come to pass. If current climate policies stagnate, we're likely to end up with warming of around 3 degrees Celsius by 2100, which is scary and tragic and far from acceptable. But this is actually good news. How? In the last decade, we've seen enough progress that most scientists now think that we have likely avoided apocalyptic climate change. Although substantial risk still remains, we can pretty confidently say that humanity isn't going anywhere. Civilization might have to change, but it will endure. Which begs the question, what has changed over the last 10 years? And is this really good news?
So what has changed over the last 10 years? Why are we in a different world now than it looked like we were 10 years ago? So 10 years ago, if we look at global emissions of CO2, which this graph shows, they were increasing rapidly. Global emissions had increased by 1/3 over the course of a single decade. China in particular had doubled its emissions and was building a new coal plant every 3 days. And the idea that the 21st century could really be dominated by coal, that emissions could continue to grow and maybe triple by the end of the century, and we could end up on a scenario like this, didn't seem that implausible. And so let's fast forward a decade later. What's happened since 2011? Well, global emissions have started to flatten out. So the red is global emissions in the period between 2011 and present. This is both CO2 emissions from fossil fuels, but also land use change from the Global Carbon Project, according to the latest values. And now it seems like instead of being on a track for a world of 4 to 5 degrees warming, under current policies, we're probably on track for a world of closer to 3 degrees warming, or a little below 3 degrees is the best estimate. As I'll discuss a little bit later, there's certainly uncertainties in this, both in terms of what our emissions might be, but also the climate response to our emissions that we can't ignore. But the central outcome of our climate projections has really changed dramatically over the last 10 years. Now, at the same time, a 3-degree world is not a world we want to live in. It's a world that's potentially catastrophic for a lot of human and natural systems, even if it's not, necessarily the catastrophe for civilization as a whole. And we need to do a lot more to move emissions down, to further bend that curve of emissions to make deep mitigation scenarios where we keep warming well below 2 degrees, a reality. But the good news for us is it's a lot easier to bend that curve down from the red line than it would be if we were still back up here and heading toward a world of 4 to 5 degrees. So what has changed? Why are we in a world that is heading toward 3 degrees? Well, a big thing is our expectations of future emissions have changed. A lot of that has to do with fossil fuels. So previously, there was a sense that we're heading toward this high-end world of 6 times more coal being burnt by the end of the century, 3 times more emissions. That's the pathway a lot of people thought we're on. In the real world, we've seen some big changes. So global coal use peaked back in 2014 and has been slightly declining since. Clean energy is getting cheaper. And if you look at the latest projections from the International Energy Agency, it seems like we're heading toward more moderate levels of emissions over the next few decades. This figure is from a paper that Glenn Peters and I published in Nature 2 years ago. We essentially argued that we need to stop using this worst case no policy scenario as the most likely outcome. That still can be useful for certain circumstances for evaluating big effects on the climate, hitting the climate with a big hammer, so to speak. It can be useful for looking at sort of extreme cases if we get unlucky with a lot of other climate responses, but it is no longer the outcome that society is likely headed toward. And at the same time, we've started seeing a huge amount of commitments by countries to do better. So we're no longer in a business as usual world, in part because countries have started making really strong commitments to reduce their own emissions. So this is from a piece in Nature we published earlier this year, where we looked at the full range of outcomes in the most recent IPCC report in terms of temperatures, and then looked at the literature of what would be implied by current policies, so policies that are in place today in countries, 2030 nationally determined contributions under the Paris Agreement, so essentially what countries have pledged to do by 2030 as part of their official Paris Agreement commitments, and then more recently, what happens if countries meet their net zero pledges? Because what's really changed for this graph in the last 2 years is countries representing over 80% of global emissions have now committed to get to net zero in the latter part of the 21st century. And this includes countries like China, India, Japan, South Korea, Brazil, the US, EU, Australia, etc. Now, it's one thing to say you're going to do something by 2050 or 2070. It's a different thing to actually put yourself on a track to do that. And we should definitely take these sort of long-term net zero commitments with a proverbial boulder of salt. But at the same time, we finally have commitments by countries that are consistent with the size of the problem, that if they're undertaken at scale, would put us on track to probably limit warming to around 2 degrees or below. And that's a much better place than we were in 2 years ago. This is a sort of big literature review we did on the subject, where we looked at all of the studies of current policy outcomes, which are in red here, of 2030 nationally determined contribution outcomes, which are in orange, and of net zero commitments, which are in blue. And here we looked both at the uncertainty in emissions, which is sort of the bars, and the uncertainty in the climate response to those emissions, which is the whiskers. And the important distinction there is there's some uncertainty in what emissions trajectory the world will actually be on in each of these scenarios. But there's also some uncertainty around how the climate will respond to those emissions, how sensitive the climate is to greenhouse gases in the atmosphere, the sort of mix of feedbacks that affect the climate and temperature response to that, and potential changes in carbon cycle feedbacks that affect how the ocean and land can take up the CO2 that we emit. Now, what's changed? Why are we heading toward a world of much lower emissions? Why are global emissions flattening over the last decade? Why aren't we headed toward a 21st century dominated by coal? One of the single biggest ones is that there's an energy transition rapidly gaining steam that's driven by the falling cost of renewables and batteries. So in the last decade, the cost of onshore wind has fallen by 60%. The cost of offshore wind has fallen by 61%. The cost of solar panels has fallen by a staggering 89%. And the cost of batteries has fallen by 83%. And this dramatic decline in costs has triggered a huge increase in the adoption of these technologies. We're at the point today where solar is actually cheaper than fossil fuels for new generation in many parts of the world. Now, obviously, there are challenges if you want to provide 100% of the grid with solar, and it's going to be harder to get to really deep emission reductions. But at the margin today, these have a huge impact on the decisions countries are making around what type of power plants to build and how to power their societies. And so as a result of these falling costs, which again are shown up on the top here for a slightly longer period of time since the year 2000, this is a figure from the recent IPCC Working Group 3 report. We've also seen a huge exponential increase in the adoption of each of these technologies in photovoltaics, in onshore wind, offshore wind. less in concentrating solar panel power, mostly because photovoltaics have become much cheaper. So there's not much reason to build CSP plants if you can build PV. And a huge uptake in the adoption of electric vehicles. In fact, this past quarter, electric vehicles were 13% of global vehicle sales, which is a dramatic increase from 5% the previous year. And we expect that trend to not slow down anytime soon. Now, some countries are doing better than others in that regard. The US, it's only 5% of new vehicle sales, so we're very much a laggard, whereas Europe, it's 20% or so, China is 18%. So we have a long way to catch up there, but we're finally reaching the point where a lot of these technologies are becoming cost-effective with fossil fuel alternatives, such that you can save money today if you buy an electric car, and to be honest, it might perform better than the gasoline car you previously had. And because of this energy transition, we've really seen a dramatic decline in the fortunes of coal. Now, coal is the dirtiest fossil fuel, and it's also the critical element to the highest future emission scenarios that we have. The real doomsday climate scenarios are ones where the 21st century is dominated by coal. And so what this graph shows is global coal use. This is from the International Energy Agency. The black line is the actual use of coal in each year. And then those colored lines are what the IEA thought would happen in each year in their flagship World Energy Outlook report under their stated policy scenario. So back in 2013, they thought, oh, coal's going to keep growing, slow down a little bit as countries start caring more about climate change, but it's got a long way to grow. 2014, they thought the same thing. 2015, they're like, well, it's not growing as fast as we thought, but it's still going to grow. 2016, 2017, 2018, 2019, you can see that almost every year, at least until the last few, where it's too early to tell, the growth of coal has been much slower than was predicted by these global energy models. There's an even more dramatic change in places like the United States. So this is the same graph, but for the US instead of the world, and looking at the projections from the Energy Information Agency, which is the Department of Energy group that's tasked with doing near-term projections of the energy system in the US. And again, here is every year since 2010, they publish an annual energy outlook where they project what's going to happen to US coal. And every single year, it continues to fall. In fact, US coal use has fallen by 60% in the last 13 years, which is one of the more rapid energy transitions of any technology we've seen in the world. And that has been a big driver for declines in US emissions, which have fallen close to 20% since their high in 2005. At the same time, we've also seen a decoupling of economic growth from emissions. So previously, many people thought that it was impossible to grow economies without increasing CO2 emissions at the same time. They were so wedded to fossil fuels, there was a necessary relationship between economic growth and emissions of CO2. And that led to a lot of people proposing radical alternatives like degrowing the global economy is the only way to effectively solve climate change. But over the last few decades, in particular, in the last 15 years, we've seen some pretty dramatic examples of decoupling in action, of countries that have increased their economic growth, which is shown in red here, and decreased their emissions, which is shown in blue. So Denmark has decreased its emissions by 45% while growing its economy 17%. The UK has decreased its emissions 37% while growing its economy 21%. And so we've identified 32 countries that have absolutely decoupled their CO2 emissions from their economic growth, which is good news. But you might look at this and say, okay, that sounds great for those countries, but aren't they just shipping manufacturing over to China? Aren't you just offshoring emissions? Is this really looking at the big picture? But what's interesting is we actually have data on not just the CO2 emissions that happen within countries, but also the emissions embodied in trade. So how much you import from countries like China that have a dirtier grid and how much you export to countries like China. And if you incorporate the emissions embodied in trade and calculate a separate metric called consumption emissions, so the emissions associated with all the goods consumed in each country, the picture doesn't fundamentally change. We still see the same 32 countries have also reduced their consumption emissions, shown here in teal, while increasing their GDP. And so it's not an issue of sending emissions overseas and just obfuscating the reductions at home. These are real reductions that we've seen in many countries that are persistent over the past 15 years. This does not include 2020. If I did, these drops would be much larger, but obviously 2020 was anomalous for many reasons, and we don't have necessarily all of the consumption emission data for 2021 yet. So it only goes through 2019 for now. And we see, concrete examples in individual countries. So this is the United Kingdom, which has, again, increased economic growth by about 21%, while reducing both territorial and consumption emissions pretty dramatically. And the United Kingdom in particular has done much of this by moving away from coal. Coal use in the United Kingdom is now down to 1800 levels, and its overall CO2 emissions are down to about 1860 levels, which is pretty impressive for the cradle of the Industrial Revolution. And a lot of this is being driven by a huge amount of resources and money that is going into the clean energy transition. This is a figure by the folks at Bloomberg New Energy Finance, who are some of the best in tracking these long-term trends. And it shows the amount of money being spent every year on mitigation technologies, on technologies that can reduce emissions. And back in the early 2000s, it was pretty small. It was under $100 billion a year. And it's risen pretty dramatically since then. In the most recent year, in 2021, the world spent about $755 billion on technologies that reduce emissions, much of those on renewable energy and electrified transport, with a smaller amount on things like electrified heat, nuclear, sustainable materials, and a tiny fraction on things like energy storage, hydrogen and carbon capture and storage. And as I mentioned, we've also seen dramatic changes in electric vehicle uptake. So this is for 2021. So I previously mentioned in the last quarter, 13% of global vehicle sales were electric. For the entire last year in 2021, it was 9%. So this is lagging a bit, but 44% of new buses sold globally were electric buses. 42% of 2- and 3-wheel vehicles were electric globally, but only 1% of vans and trucks were electric. And so we're seeing a dramatic increase in the uptake of some of these, but we still have a long way to go. And what we're really seeing here, and how I like to think about it, is a virtuous cycle of technology, behavior, and policy. So let's start with technology here. As we get cheaper clean energy technologies, we get cheaper electric vehicles, we get cheaper heat pumps, it becomes a lot easier for people to change their behavior around those technologies. I'm going to be a lot more willing to buy an electric car if it only costs $1,000 more than a conventional car up front, than if it costs $10,000 more. I'm much more likely to get a heat pump for my home if it is around the same cost as a conventional thing. And so the bar for changing behavior falls, and we get much wider spread consumer adoption as technology drives clean energy costs down. At the same time, technology enables policy. So the reason why countries like China and India are willing to set a net zero target today, which they certainly weren't willing to set a decade ago, is because they see a pathway to reduce their emissions to zero later in the century, while not coming at the expense of their development goals, while not coming at the expense of lifting hundreds of millions of people out of poverty. And again, that's because it seems like the cheapest option in the future for many sectors is going to be technologies that don't emit carbon dioxide, that don't burn fossil fuels. At the same time, behavior also affects technology and policy. So as people are more willing to pay a premium for clean energy technologies because they're concerned about climate change, they will help drive the cost of those technologies down. The fact that people were willing to spend so much money for Teslas a decade ago is one of the reasons they've gotten substantially cheaper today, because they get those economies of scale through early adopters. Similarly, behavior can influence policy. As more people get concerned around climate change, they increasingly call their representatives, they get out in the street, they vote, and they create policy changes. And then finally, policy has a critical role in influencing both technology and behavior. Many of the clean energy technologies, such as solar panels and electric vehicles, benefited substantially from early policy support. Particularly solar panels in the 1970s were pioneered out of US national labs. And policy can have an effect on behavior through changing rules and regulations, through enabling alternatives, and through allowing people to act in different ways. So those are all related. And we've finally started seeing a lot of countries adopt more meaningful near-term climate policies. So one challenge we had for a while was we were seeing countries have these long-term 2050 net zero targets, which are laudable. But again, there wasn't really a pathway to get from where we are today to a net zero target in 2050. And what's changed in the past year in particular is we've increasingly seen countries set stronger near-term decadal targets around their emissions. So the Inflation Reduction Act was passed in the US a few months ago, and that is hopefully going to get us a 40% reduction in US emissions by the year 2050. We saw Australia pass a similarly strong climate policy. China has significantly upped its domestic targets for renewables. We saw Europe pass their own version of a Green New Deal that sets strong policy for the next decade. And so we're really starting to see strong movements toward reducing emissions. And this can really have ripple effects across the economy. This is a quote from a recent piece that was published in The Atlantic by Robinson Meyer, who essentially says that, if it's adopted at scale and leads to the changes we'd expect, the Inflation Reduction Act could really change a lot of these societies and make climate-related industries a giant space in the US. And it's still, we have to wait to see exactly how much of this comes true, but certainly we're talking about changes at a scale today that we have not seen in the past. Another area and reason I'm hopeful is that we're increasingly understanding that there's not necessarily global warming locked into the system, global warming in the pipeline that's inevitable, that ultimately we, due to our emissions, have a large amount of control over how much the world warms. And the idea of warming locked in or in the pipeline has long been something that's in the public consciousness. In fact, until last year, NASA even had a page that said there's 0.5 degree warming in the pipeline. And the reason for that confusion is because until recently, most climate models were not Earth system models. They didn't have biogeochemistry. They didn't have the ability in the model itself to translate emissions into atmospheric concentrations. And so when climate models ran experiments to see what would happen in the future, they would hold atmospheric concentrations of CO2 constant. They'd say, if we keep CO2 at 420 parts per million, the world is going to warm by about 0.5 degree over the next century, which is true. But what's important to note here is that holding CO2 concentrations constant is a very different thing than getting emissions down to zero. And the reason is, if we get our emissions down to zero, CO2 concentrations start falling because land and ocean sinks take up more carbon than we're emitting to the atmosphere. And so while a world of constant concentrations leads to increasing warming over the next few centuries, a world of zero emissions actually leads, in most of our models, to roughly flat temperatures. So this is a simulation of what would happen if we got to zero emissions this year. Obviously not completely realistic, but a good diagnostic simulation for climate models. It's based on some work by Matthews and Weaver back in 2010. But essentially, you would end up with largely flat global temperatures at current levels. So why does that happen? Why does global warming stop once we get emissions to zero? Well, it turns out what's happening in the climate system is two things, and those two things largely counterbalance each other. First, once we get emissions to zero, the land and the ocean keep taking up more CO2 from the atmosphere. So atmospheric CO2 concentrations start falling quickly at first. Eventually, they level off. And that by itself would cause cooling. That's the blue and the yellow bars in this diagram, which is the change in the energy flux across 18 different Earth system models in scenarios where you have zero emissions. So by itself, falling atmospheric CO2 concentrations would lead to cooling. But at the same time, the Earth is out of thermal equilibrium today. The oceans take a long time to warm. And so even as CO2 concentrations in the atmosphere are falling, the oceans are continuing to absorb heat since they're catching up. The deep ocean is still much cooler than the surface ocean, has not absorbed nearly as much heat. And because ocean heat transfer is slow, the world sort of keeps heating up even once you get emissions to zero. And if you look at the temperature effects, the actual warming you get across these 18 Earth system models, some of them show cooling after the point of zero emissions, up to 0.3 C or so. Some of them show warming after zero emissions, up to 0.3 C warming or so. But most models show around zero change or around 0 degree zero emission commitment, as we call it, which is good news. Again, it means that we ultimately have control over how much warming we experience. And these findings hold both in scenarios where you immediately drop all emissions to zero, which is not particularly realistic, or in scenarios where you gradually decrease emissions to zero. You still end up with similar warming trajectories after the point of zero. So it's not necessarily that sensitive to the trajectory to get to zero. The caveat with this is that these scenarios have generally only been run in deep mitigation outcomes, where you're trying to limit warming to below 2 degrees. If we were to get to a world of 3 or 4 degrees warming and then hit zero emissions, it's possible that we could trigger things like permafrost feedbacks that would have larger amounts of long-term warming than are captured in these models. So, let's not do that. And then finally, we talk a lot about CO2, but obviously CO2 is not the only game in town. And what actually happens to the climate ends up being, to a large degree, a function of other greenhouse gases as well, particularly non-CO2 greenhouse gases like methane and nitrous oxide, but also aerosols, which have a strong cooling effect on the planet right now. And so this is adapted from a figure in the IPCC Special Report on 1.5C in 2018. It essentially shows 4 different scenarios from today. The first is the blue line, where you get to zero CO2 emissions immediately, but hold everything else constant, hold aerosol concentrations constant, or aerosol forcing constant, hold methane and nitrous oxide concentrations constant. And again, as we saw earlier, you get pretty flat temperatures. But there's other possibilities. If we're in a world where we go to zero CO2 and get rid of all the aerosols, many of these aerosol emissions are coming from power plants that are also emitting CO2, so it makes sense that aerosols will decline pretty rapidly with CO2 reductions. We actually get a pretty big warming of about 0.5 degree C. And again, that's because aerosols are masking a lot of the warming we're experiencing today. However, if you end up in a world where you cut all greenhouse gases to zero and hold aerosols constant, you get pretty rapid cooling. And the reason for that primarily is because of methane, which is a very strong greenhouse gas, but also a very short-lived one. Most of the methane we emit today drops out of the atmosphere in about 10 years. And so once you get rid of methane, you have a pretty rapid cooling effect, again, of about 0.5 degree C. And so it turns out if you look at a scenario where you go to zero greenhouse gases and zero aerosols, these two effects somewhat cancel each other out. They're not perfectly temporally aligned. You probably end up with a bit more cooling because the methane forcing is stronger than the aerosol forcing. But you get this purple line here, where you get a short-term bump due to aerosols falling out and then a long-term decrease due to methane reductions. Obviously, all of these are very simple idealized scenarios. In any world, we're not going to get to zero emissions tomorrow, and you can look at lots of different combinations of these things. But the general point is that there is not necessarily a huge amount of additional warming inevitable, particularly if we focus on cutting short-lived climate pollutants like methane alongside reductions in CO2 and aerosol emissions. It's also worth noting that these reduction in aerosol emissions that cause additional warming in scenarios are already baked into a lot of our models. So all of the deep mitigation scenarios we look at in the IPCC report, like the SSPs, SSP 1.1.9, SSP 1.2.6, the old RCP 2.6 scenario, they all assume a strong decline in aerosol emissions in the coming years, like 80% or so. And so we're already accounting for aerosol warming in all of our future emission mitigation scenarios. The other thing that's changed over the last year or two that has a big bearing on our expectation around future warming is a narrowing of the range of climate sensitivity. So climate sensitivity has long been a bit of a holy grail for the climate science community. And when we say climate sensitivity, what we generally mean is how much warming we get if we double the amount of CO2 in the atmosphere and let the system run to equilibrium. So again, double CO2 concentrations, hold it constant for a couple hundred years, and then you get the warming the system experiences. The first estimate of climate sensitivity was published by Jules Charney back in 1979. And he said at the time, in a report to the Carter administration with a number of other scientists, if we double the amount of CO2 in the atmosphere, the world will likely warm somewhere between 1.5 degrees and 4.5 degrees, with the best estimate of around 3 degrees. Now, fast forward 20 years after that, or 30 years after that, I should say, in the IPCC fifth assessment report published in 2013, they said, if we double the amount of CO2 in the atmosphere, the world will likely warm somewhere between 1.5 degrees and 4.5 degrees. They didn't give a best estimate in that report, but in the fourth assessment report, they said the best estimate is 3 degrees. So the fact that that hadn't changed in 30 years was not a great look for our community, even though arguably Charney was far too confident in the range he proposed back in 79. What has changed, though, is in the most recent IPCC report, the sixth assessment report, we effectively cut the uncertainty in climate sensitivity in half. And the way we ended up doing that was to look at a combination of multiple lines of evidence. So take evidence from paleoclimate studies of the Earth's distant past, the last glacial maximum, the Eocene, take studies of physical process models, of cloud behavior, of climate models, and take observations. How have global temperatures actually changed? How has ocean heat content actually changed? And it turns out that those estimates are largely independent of each other. And because they're independent of each other, the joint probability of those estimates ends up giving you a narrower range than if you look at any of these individual estimates of climate sensitivity in isolation. And so by combining these different independent estimates and using some Bayesian magic, we ended up reducing the range in the most recent IPCC report to 2.5 to 4 C as the likely range of warming, with a best estimate still of 3 degrees. And that means that we're both less likely to get lucky and have low climate sensitivity and little warming, but it also means we've slightly narrowed the high end, that we're less likely to get super unlucky and end up with much more warming than we expected. And why this matters is even in a world where we think we're on track for a good climate outcome, even in a world where we think we're heading toward, say, 2 degrees C, there still is a chance that you end up with much more warming than that. So what this wheel on the left shows is the probability of different warming outcomes in a world where countries meet their 2030 Paris commitments. So to remind folks, this would be a world where the mean expected warming is about 2.5 degrees, but you still have, you know, a non-trivial chance of 3 to 4 degrees warming, about a 20% chance, and maybe a 2 or 3% chance of 4 degrees plus warming. And again, this is because we don't have a perfect understanding of climate sensitivity or carbon cycle feedbacks. And even in a world where we think we're heading toward 2 degrees, which is this world of net zero targets on the right, there still is a small chance of ending up between 3 and 4 degrees. And so when we're thinking about setting targets around climate change, of deciding how much we want to reduce emissions, we shouldn't just focus on the median outcome of the most likely outcome. We should focus on these tail risks. Because if we think we're heading to 2 degrees and end up at 3.5 degrees, you know, that's a really catastrophic outcome for the planet. And it's one we should try to minimize by reducing our emissions as quickly as possible. Another way to think about it is that there's really 3 sources of uncertainty when we're trying to project future warming. This is a figure I put together a couple years back to try to explain this, and it looks at the old RCP scenarios. So RCP 2.6 is a scenario of deep mitigation. We're limiting warming to about 1.7 degrees by 2100. RCP 4.5 is a world of about 2.5 degrees warming. RCP 6 is a world of 3 degrees warming, and RCP 8.5 is a world of 4.7 degrees warming or so. Now, if we just had emissions and did not have to worry about any of the other uncertainties in the climate system, we'd know precisely where the climate warming would end up. But that's not the world we live in. We have 2 other uncertainties. The first is climate sensitivity uncertainty, which adds, you know, about a degree of uncertainty plus or minus to those central estimates, a little bit more in very high emission scenarios. And then on top of that, we have uncertainties in carbon cycle feedback. Because as the world warms, we expect the ability of the ocean to take up our extra CO2 to decrease. We expect the ability of the land to take up CO2 to decrease due to more wildfires, more soil moisture loss and droughts, though that's somewhat compensated by higher levels of CO2 that can encourage plant growth, so the uncertainty of land sink is slightly bigger. But we don't precisely know how these systems will respond to a warming world. And so there's some uncertainty in those systems that is added on top of the uncertainty in climate sensitivity. And so even though we think we're heading toward, say, a 2.5 degree world here, we could really end up in a 3.5 degree world if we sort of roll 6s on all the climate tests. And, you know, we have to emphasize the path ahead of us is daunting. You know, the world has set a target to limit warming to 1.5 degrees, or at least well below 2 degrees. There's a few different ways of interpreting that target. And what this graph shows is, given the remaining carbon budget, essentially how much could you emit before you pass these different levels of warming relative to pre-industrial, what would an emissions pathway have to look like to stay within that carbon budget? So if we wanted to limit warming to 1.5 degrees with a 66% chance, we'd have to get global emissions down to 0 in the late 2030s. If we wanted to get to 1.5 degrees with a 50% chance, we'd have to limit, or we'd have to get emissions to 0 in the mid 2040s. And then if we wanted to limit warming to 2 degrees with a 66% chance, so that's a central outcome about 1.7, 1.8 degrees C, we'd have to get global emissions to 0 in the mid 2070s. And then for a 50-50 shot at 2 degrees, we get global emissions to 0 in the mid to late 2080s. Now you can extend the point of 0 emissions a little bit if you let these lines go negative, if you start removing more CO2 from the atmosphere than you're emitting. And a lot of our scenarios, particularly those that limit warming to 1.5 degrees, do deploy a lot of negative emissions because, to be honest, no one believes these blue or green curves are actually going to happen. But even then, if you extend them a bit and try to get global emissions to 0 in 2050, it's daunting. And then this is that same graph, but put into a longer perspective. So this is all of human CO2 emissions from 1750, when we sort of first, started being able to get estimates of this. There might be some land use emissions before 1750. People argue about that a bit, but this is the trajectory of human CO2 emissions since then. And to put in perspective, if we want to limit warming to 2 degrees, we have to reduce our emissions about as quickly as we increase them historically. And if we want to limit warming to 1.5 degrees, we need to reduce our emissions 2 to 3 times faster than we historically increase them. Now, I should emphasize, as I said at the beginning, that these are targets. And these are targets that are set through, to be honest, a somewhat arbitrary and political process. There's no physical limit at 1.5 degrees that goes from fine to there be climate dragons. But at the same time, the further we press the climate past the range it's been in the last few million years, the bigger the risk of unknown unknowns. We don't have great analogs to a world that is 3 degrees warmer than today. We have the last interglacial, which was 1.5 to 2 degrees warmer than today. We didn't see any giant climate tipping points at that point in time. But I certainly don't want to make a bet and see what happens if we press the world to 4 or 5 degrees. To put in perspective, the last ice age, which was a very different planet, was about 6 to 7 degrees C cooler than today globally. And so any of these global figures we're talking about, be it 1.5 C or 2 C, can hide a huge amount of regional variation. In general, for example, the land is warming about 50% faster than the world as a whole. And areas that are more landlocked or more high latitude are warming historically faster than that. So I want to show one more quick video, and I might have to adjust the volume here really quick.
Next few decades. So everything's fine then? Well, let's not get carried away.
Whoops.
Next few decades. So everything's fine then? Well, let's not get carried away. All of these processes are great, but not nearly fast enough. We're still doing way too little, and technology will not magically solve everything. We need to use fewer resources and use them longer, design consumer goods that are repairable and durable, and decrease our energy requirements. We need much better infrastructure, agriculture, and cities. It will still be hard work, especially to get the right policies passed and enacted. But for the first time ever, there are a few trend lines pointing solidly in the right direction. And now imagine if all of this was achieved without proper financial and political support, and despite fossil fuel lobbying. Just think what humanity can do when climate change finally gets the political attention and funding it needs. So is it okay to feel hopeful again? The situation is still dire and serious, so what's the point of focusing on this side of the story? The trap of hopelessness. Climate change can feel overwhelming and make your future seem bleak. The sadness and hopelessness that many people feel is real and very destructive because it causes apathy. Apathy that is only serving the fossil fuel industry, that is still delaying change however it can. In a sense, they have weaponized hopelessness. We are now in phase 4 in the public debate about rapid climate change action. Phase 1 was, climate change is not real. Phase 2 was, climate change is real, but not caused by humans. Phase 3 was, climate change may be caused by humans, but it's not that bad. Phase 4 is, climate change is no longer avoidable. We are doomed, and it doesn't matter what we do. If we want the world to change, we first need to believe that change is possible. And we have an abundance of evidence that it is. Changes to our industrial system are gaining momentum. Technology gets better and cheaper. Climate change has become a key issue in most free elections. As more and more younger people move into influential positions, they prioritize climate change and work on new solutions. In 2022, most governments not only acknowledge it, but set their own net zero goals in democratic and autocratic countries. The results of years of fighting a steep uphill battle are now clearly visible. The pressure needs to keep increasing to make sure that the promises made today are actually kept. Climate doomerism is the equivalent of giving up, even though you can still prevent not just the worst case, but also mitigate most of the bad things, make changes in time to adapt better, and prevent the poorest from suffering. That is why hopelessness and apathy are so dangerous. If the last, in many ways, wasted decade has shown anything, then it's that progress is being made, and that dire scenarios are just predictions, not our sealed fate. As of 2022, based on current global policies, we will end up in a 3 degrees world. Now it's our job to yet again prove the predictions wrong, despite how serious and urgent things are, to turn that 3 degrees into a 2 degrees and then see where we can go from there. For that, we need hope. And we hope we gave you that today, at least a little. That you feel that things are serious, but also that you have a future. That you can have kids without dooming them or the world. That taking action today is worth it. And that despite powerful industries doing everything to delay it, society is changing. If you need a more concrete roadmap of what you can do personally, we're working on a follow-up video to talk about that in greater detail. Doomerism, inactivity, and weaponized hopelessness are the only trump cards left for the powers that don't want change. Don't let them win.
Okay. Oh, there we go. They can do a much better job of explaining than I can. But yeah, so as I mentioned at the start, I've definitely seen a rise in doomerism, a rise in hopelessness. An interesting example of this actually is some of my work on future emission scenarios was quoted earlier this year by Ezra Klein in a column he had around why climate change is not a reason not to have kids. It's a double negative, but why we shouldn't let climate change be a reason to not have kids. And the reaction to that was startling, both for myself, but particularly for two of my female colleagues, Kate Marvel and Leah Stokes, who are also quoted in that column. And the huge amount of people were very angry that we had the temerity of saying that our children are not necessarily doomed to an apocalyptic hellscape, that there's time to turn this around. And don't get me wrong, we can still screw things up. Like even a 3-degree world that seems like we're heading to right now could be reversed. You know, we could end up in a world of resurgent nationalism, isolationism, regional conflict, where people turn back to domestic energy resources like coal and roll back climate policies. It's not off the table, and neither is a world where clean energy keeps getting cheaper even faster than we expected. But we have a lot of agency in determining which of these worlds we end up in. And at the point at which we give into hopelessness, when we say it's too late, we can't solve it, it's too big a problem, that becomes a self-fulfilling prophecy. And so when I say we need a cautious climate hope, I'm really trying to sort of divide between two extremes. Either a world of blind optimism, where we say that, you know, technology is going to solve all our problems, it's going to be easy, climate change is going to take care of itself, or a world of hopelessness, where we say that, you know, there's no future, there's no way to solve these problems. And I think there's a very rich space between those two extremes to explore. And so I'll give two quotes up here. I'm not going to read the whole thing because I'll leave folks to read it themselves. But this first is from Kim Stanley Robinson, who wrote Ministry for the Future recently, which is a great sort of climate policy / science fiction book. And this is an interview he did earlier this year with Ezra Klein. We essentially said that, you know, hope, optimism, this attitude is necessary political stance to take because we're in a position of privilege and the situation can be saved. And given those two, it's a dereliction of duty to be pessimistic, to be cynical. It's just a chicken thing to do. And the other quote I wanted to give you is from Hannah Ritchie, who's an awesome researcher at the University of Oxford. She helps publish a resource called Our World in Data. If anyone here has never seen Our World in Data, you should really check it out. They do amazing data visualizations across public health, climate, energy, you name it. They do the best accessible data analysis and visualization for these things. And what she said is, you know, optimists are the ones that move us forward. They're the innovators, the entrepreneurs, the ones willing to put the reputation, money, and time on the line because they see an opportunity to solve the problem. And so I would hope that we all come out of this with a little bit more optimism that, you know, this is a problem we can solve, even if it's a very hard and difficult one. And so I'll finish with a few thoughts on where are the remaining areas that we need to focus if we really want to solve this problem. Because again, we have made progress in the last decade. We still have a long way to go to meet our most ambitious climate goals. And part of that is figuring out the areas that are going to be tough. Like we are benefiting hugely today from certain technologies, particularly renewable energy and electric vehicles that are either mature or in early adoption today. But if we really want to get to net zero, and this is a figure from the recent International Energy Agency World Energy Outlook, we don't just need the technologies that are mature today. We also need to accelerate technologies that are in early adoption, like electric vehicles, and we're going to need technologies that are only in demonstration or prototype stage today, and scale these up substantially. And these include things like industrial heat, how you can get 2000 C temperatures without burning fossil fuels. They include things like heavy duty freight, aviation, agriculture, how we control methane and nitrous oxide emissions in the context of our agricultural systems, and things like carbon dioxide removal that are going to be necessary both to deal with residual emissions in the system that we can't fully eliminate and non-CO2 greenhouse gases, and ideally to deal with any overshoot. Because while it seems certain that the world is going to pass 1.5 C in the next decade or two, that doesn't mean we can't ever go back. We know that even if we get our emissions to zero, the world doesn't cool back down, But we also know if we remove more CO2 from the atmosphere than we're adding, we can cool the planet. And that's something that climate models are quite consistent on, that the behavior of the climate is largely symmetric to the addition or the removal of carbon dioxide. And so if in the future, we say limit warming to 1.7 degrees, we succeed in getting clean energy cheap and cutting up fossil fuels very quickly, we still can bring things back down with concerted effort. And so, we need ultimately a pathway that looks sort of like this. This is a figure from the most recent IPCC report, working group 3, that sort of shows the change in global emissions of CO2, which are decreased about 90%, of non-CO2 greenhouse gases like nitrous oxide and methane that are decreased 50 to 66%, of removals on managed land and trees and forests, which continue to be a sizable part of the carbon budget, removals, and other removals through more technological means, things like direct air capture, enhanced rock weathering, bioenergy with carbon removal, etc. And so I'll finish just by talking a little bit about what I'm doing today in my current role. So as was mentioned in the introduction, I'm currently the climate research lead at Stripe. And what Stripe has done is we've partnered with a number of other technology companies, including Alphabet, Meta, Shopify, and McKinsey. And we've put about $1 billion towards scaling up carbon removal technologies in the next decade. Not because they're silver bullet, they're a 10% solution to a very big problem of climate change, but solar panels are a 20% solution. Electric vehicles are a 20% solution. Industrial heat is a 10% solution. Climate change, there's no silver bullets, there's just silver buckshot. And so we identified this as an area that has historically had significant underinvestment. And so by putting $1 billion advanced market commitment toward it, we could create companies in the space. We could, give investors the knowledge that they'll be able to comfortably invest and make a return by guaranteeing a market for these carbon removal technologies. Again, so they can play a part in ultimately getting us to net zero and beyond. So that's it. I wanted to leave a lot of time for questions and happy to answer any that folks might have.
Thanks so much, Zeke. So we will have, we have at least sort of 15, 20 minutes for questions. And I think Pete Boulay is going to help move around here. Do we have a microphone for this?
Let's test it
Okay. So it looks like we already have one or two.
I can also repeat the question for the folks on the Zoom.
Yeah, maybe we can start with that. So if you'd like to ask your question, go ahead.
Sure. My level of optimism is appreciate the talk. My level of optimism is also impacted by and then it's tipping points and negative feedback loops. And if we haven't reached, we're rapidly reaching tipping points in the Amazon rainforest, methane release of melting permafrost, temperature in the oceans, and weakening of sea ice due to negative feedback from the current warmer currents beneath that ice. So, and that's happening at less than 1.5. Now, that may not be the end of Earth as we know it, but it's going to have significant impacts going forward with massive migration of people that can't survive along the ocean or coastal lines, and recent reports showing that Asia and Africa are looking at extreme heat events that will make life uninhabitable.
So the question was around tipping points and how we should think about being optimistic or hopeful in the context of, very pressing, concerning tipping points that may already be kicking in at the levels of warming we're experiencing today. And tipping points are an area that is much discussed in the climate community, and many of which are already incorporated into our models. Things like permafrost feedbacks are in the concentration scenarios used to drive the scenarios in the most recent IPCC report. Things like Amazon savannahization dynamics are in many Earth system models, as are ocean cycle changes, sea ice loss. And so when we look at future warming projections today, we're already accounting for a number of these processes, but there are some that we're not. And there are many local and regional effects that we expect to be quite large from climate change. Coral reef ecosystems are probably going to be very severely degraded between 1.5 and 2 degrees, and we're already starting to see mass coral bleaching in many parts of the world. Ice sheets, obviously, we are locking in a long-term sea level rise over the next millennia associated with the temperature levels we have today as ice sheets melt. And we may even have up to a meter or so of sea level rise by 2100, hopefully less in deeper mitigation scenarios, but there's large uncertainties there. But what we don't really see, at least in our models today, and again, we should be humble, we may be missing things. We don't see dramatic thresholds in the climate. We don't see processes that could significantly enhance the amount of warming that we're going to experience beyond what we already see and project in our models. Now, this is an area of ongoing research. There is certainly a group of researchers who has argued for sort of a tipping point cascade or hothouse Earth hypothesis, where the combination of these factors could sort of send the Earth into a different climate regime characterized by much higher temperatures. But to date, at least, we don't have strong evidence of actual physical mechanisms to support that. And so, well, I'd say that regional tipping points and ecosystem tipping points are a very strong motivation to reduce our emissions as quickly as possible. I don't think that there's much evidence that, we'll end up in a world a degree C warmer than we thought because of some sort of climatically significant tipping point that we're not accounting for today. At least in a world of, below 2.5, 3 degrees warming. Again, if we get to 3 degrees, 4 degrees, 5 degrees, all bets are off because we don't have great analogs. Our models may not be capturing the type of events. And if we look at the paleoclimate in the Earth's more distant past, there's certainly periods of rapid changes that should be humbling for our projections of the future.
Hi, Zeke. I really appreciate your talk. Thanks. One of the classes I teach here at the U is a freshman class where we talk about climate change. And there's hundreds of students in the class, and so I feel that this sort of message of empowerment is a really important thing to make. I noticed in your talk you talked a lot about coal and renewables, but you didn't talk about which is a big part of the sort of recent emissions of CO2 plateau, especially in the US. And so I'm wondering where you see that fitting into your sort of actions.
Yeah. So the question was, how do we consider things like fossil gas or natural gas, which arguably has been a big driver of coal decline, at least in the US, less so in Europe and in the UK, but is also a fossil fuel and is actually one of the bigger drivers of increasing fossil fuel emissions since coal is decreasing. So gas is a tough one, in part because it is lower emissions than other fossil fuels, and it's a lot more flexible than other fossil fuels. So if you look at the literature on energy system models for deep decarbonization scenarios in the US, for example, you actually do tend to have a lot of residual gas capacity for a long time. And the reason for that is sort of balancing out variable renewables. But what we do see in those models is, even though the amount of gas capacity itself, the sort of number of plants might not change, the utilization of those plants falls dramatically. So today, a typical gas plant in the US is used about 50% of the time. At the point of net zero and say models by Jesse Jenkins, Chris Clack, or some of these other modelers, you have a utilization rate of maybe 5%. And then you're making up for that elsewhere in the system with direct air capture or bioenergy and with carbon removal. If you look at what models and integrated assessment models that we use in the IPCC process show, is there's really a loading order of fossil fuel declines. Coal is the first to drop, then oil as we largely switch to electric vehicles, and then finally, gas slowly declines and then declines more rapidly later on as we, build new buildings with heat pumps, as we retrofit existing buildings, and as we, fully move gas out of the power system. And so, I'd say in the near term, we should certainly not be building new gas. We should clean up the leaky methane problem in the oil and gas system, which is a huge issue and one that thankfully the Inflation Reduction Act takes some strong policies around. And we should plan, to the extent we're using gas, to try to minimize that, even as we focus on getting rid of coal quickly.
I got the mic here. I have a question for you about that. You got a sort of virtuous cycle laid out: policy, technology, behavior. I'm curious how you think about what's the worst case scenario with regards to policy. I think there's a tendency, both in like that Ezra Klein interview, in the videos you showed, to think of the last 10 years as sort of a worst case scenario policy-wise. So we didn't get a lot of, certainly in the US at least, we didn't get a lot of policy directly involved in climate due to political paralysis. But I think one of the things that sort of informs my lack of optimism as you look forward is I think it might be wrong to think the last 10 years as sort of the worst case scenario for policy. I think that we start thinking of that as one of the better cases where at least there wasn't necessarily opposition. So in the context of the world, you do have a reference in your talk to Putin's war and to the effects that's going to have. In the United States, more directly, we have sort of the end of the post-Nixon agreement, so the end of the Clean Air Act, Clean Water Act on the near horizon, the beginning of Schedule F, which would be the end of U.S. civil service that can tackle these issues in sort of a political way. So I'm curious what you think, how you think about what are those true worst case scenarios for policy, and how do we move forward? What are the chances of moving forward in a world where policy isn't just neglectful, but actively hurtful?
That's a great question. And again, the question was, how do we think of what is the worst case outcome for policy? And might that be a lot worse than the sort of policy paralysis we faced over much of the last 10 years? And I think you raised a really good point. One of the scenarios that really resonated with me that was developed in the run-up to the most recent IPCC report is called SSP3. And what SSP3 is a world of resurgent nationalism and isolationism, regional conflict, where countries turn toward domestic energy resources. I got in a bit of trouble when the Washington Post quoted me as calling it Trump world, but it's not too far off, to be honest. And so we could certainly imagine a world where we actively roll back existing climate policies, where we ban the development of new solar and wind, as the UK is trying to do right now on its farmland for solar, which is madness. And where we're actively subsidizing fossil fuels, as the Trump administration tried to do with coal. Thankfully, what makes me a little confident is A, that didn't actually pass in the Trump administration, and B, clean energy has become cheap enough that you're paying a large cost to actively go back to fossil fuels. The place that has installed more renewable energy than anywhere else in the United States is not California, it's Texas. And the reason is because they have a deregulated power market, and wind and increasingly solar are by far the cheapest option. And so they're building ridiculous amounts of them. Red states are actually the main source of wind generation in the US today, particularly in the Midwest. And so, there is a world where, as long as polarization doesn't win out over pragmatism, or certainly doesn't win out over economic self-interest, a lot of these trends are going to push politics in the right direction, simply because clean energy is going to become a giant employer in red states. For better or worse, some people developing electric vehicles are now identifying as Republican and getting into the culture wars in a weird way. And, I don't think there's necessarily going to be a future where we keep having climate as a central polarizing issue. Now, there certainly is a risk that we end up embracing a different politics of climate on the right that's equally problematic. There's concern around sort of fortress worlds where rich countries turn in onto themselves and, keep climate refugees out. And, there's a great essay by Niels Gilman on what he calls avocado politics. That's definitely worth reading. But, I'm a little hopeful that as clean energy becomes big business, it's going to have the power of big business in shaping our politics, and that'll create a lot of inertia that's hard to roll back.
We have some online questions that I'd like to get to. So Alejandro, after this one. So we have Eric Steig, who's professor and chair at Department of Earth and Space Sciences at the University of Washington, ice core scientist, the person who got me into research. He wonders whether the narrower uncertainties on equilibrium climate sensitivity really apply to Earth system climate sensitivity. Doesn't the long tail of uncertainty remain on the longest timescales?
So that's a good point. So when we talk about climate sensitivity, there's three different elements. There's the transient climate response, which is sort of the short-term response to increasing CO2. There's the equilibrium climate sensitivity, which is the sort of centennial scale response to doubling CO2 concentrations. And then there's the Earth system sensitivity, which is what if you hold it constant for thousands of years, then you have ice sheets melting away, you have large-scale albedo changes. The one bit of comfort I take around that is the way that Earth system sensitivity over long scales would be traditionally defined as holding CO2 concentrations constant for thousands of years. And as I discussed earlier, holding CO2 concentrations constant is sort of a weird construct. It involves reducing emissions, but not getting rid of them, and keeping enough residual emissions to balance sink behavior. And so, I think that if we can actually get to a world where we get to zero emissions instead of constant concentrations, we'll end up with outcomes that are, hopefully better than would be implied by Earth system sensitivity for current concentration levels. Obviously, there's Earth system sensitivity for lower concentration levels that would emerge in a zero emission scenario, which is still worrying. And there's sort of bigger thorny questions about how we sort of value society thousands of years from now relative to society today in terms of impacts. But certainly, climate operates over a very long time frame. A ton of CO2 I put in the atmosphere today, it's going to take almost 500,000 years to fully remove it. And so, we are sort of creating impacts for generations to come with our actions today that'll be hard to reverse. And it's definitely worth keeping that in mind.
Okay, I'm conscious we have a few more questions online, so we do Alejandro and then one more online question.
Yeah, quick. Thank you for your talk. We hear a lot of talk recently about nature-based solutions, and that's a really exciting part of the market. But the problem I see with a lot of these solutions, like enhanced rock weathering or ocean solutions, is that measurement and validation of what carbon they're actually capturing in real time is really difficult. So therefore, it's difficult to get money from big financial actors to invest in these things where they can't really prove that carbon has been pulled. But a lot of the proponents of these technologies are, all about them. And I was just wondering how you see that going into the future, how you see more people investing in these things that seem, optimistically like good options, but cannot be proven like direct air capture can.
So the question was, how do you think about carbon dioxide removal approaches that are hard to directly measure and that have potentially high levels of uncertainty? And how do you balance those against more certain approaches like direct air capture? It's a great question. To give a little plug on some work we did recently, we recently launched a tool with an organization called Carbon Plan on MRV uncertainty mapping for carbon dioxide removal pathways. And provided some guidance around how to sort of try to account for uncertainty in open systems like enhanced rock weathering, like ocean CDR, where there is a lot of potential points where you could lose some of the reductions through, say, if you're doing enhanced rock weathering, you can have evasion if the dissolved inorganic carbon interacts with low pH environments and streams and estuaries before it reaches the ocean. There's secondary precipitation of calcium in the context of ocean alkalinity enhancement that's a worry. There's different points where you could have some of these carbon dioxide removal approaches be less effective than you thought. And so there both is more research that needs to be done there, but also at some point you need to balance the uncertainty with the scale and the cost. It may well be that something has a 30% uncertainty, but it's half the cost of direct air capture. And that might be something that's worth pursuing. So definitely check out the Carbon Plan tool and the accompanying analysis there.
Okay, so I'll take one more question from online. We are going to start eating into our time for reception, but I think it's great we have Zeke here with us, so long as you're not running out of steam with all the questions. Merle Davis Matthews online asked a question that I feel like I hear often is, as somebody who works with mining impacted communities, I have less optimism about electric vehicles. We know that Indigenous people often face the worst of climate change and are now being asked to become sacrifice zones to the green economy. How do we account for this as we face the need to transition away from our current economy?
It's a great question. I mean, one of the biggest challenges with getting, or actually I should repeat the question first because I'm not sure folks in Zoom heard it. So the question is, how do we avoid the impacts, particularly on disadvantaged communities and Indigenous communities associated with the energy transition? The need to mine lithium, the need to build new infrastructure, all that sort of stuff. And it is a real challenge. To decarbonize our economy quickly enough to avoid the worst impacts of climate change, we're gonna have to build a huge amount of things, much faster than we have before. Transmission, electricity generation, electric vehicles, and that requires a lot of stuff. It requires a lot of lithium, it requires a lot of steel, requires a lot of concrete, requires a lot of fiberglass, polysilicon, and all those have to be produced. And so there's been this idea in the environmental community for a long time that sort of small is beautiful, that the solution to climate change is, a solar panel on every roof and a wind turbine in every backyard. And an electric bike at every garage. And certainly that's part of the solution. But in a lot of cases, decarbonization is also going to be big and ugly. And there is going to be a need to produce more materials, to build more things, to take a lot of land to build those things. It's probably going to take a couple % of total US land area just to have all these wind turbines and solar panels to power our grid. And that has real impacts. And so the question then is, how do we minimize those impacts? How do we promote best practices? How do we figure out ways to, say, extract things like lithium that minimizes the impacts in local communities? And there is work being done to that end. So for example, California has a big project in the Salton Sea to pioneer a much more ecologically sustainable form of lithium extraction that should have much less impacts on land. But there's also challenges around where we draw lines. So for example, today, a lot of our lithium is produced in Bolivia. There's discussions around expanding lithium production in areas in the US. There's tribal communities that are divided on this issue. Some support the development, some oppose it. But there's also a question we have to ask ourselves, which is if we do not develop this in the US, and I think most people would agree that US mining has stronger safeguards than around much of the outside of the world, are we just pushing the development of these minerals into more disadvantaged communities overseas that might not have a say in the process? And so I think it's incorporating community input, pioneering best practices, and figuring out a way to minimize the impact as we build a lot of things quickly to move away from fossil fuels. But there's no easy answers there. It's a tough and thorny issue, and we do need to take local community concerns seriously.
So I might make the executive decision that we can continue questions after one more online. Those of us who are here can pester Zeke out at the reception. Good luck, Zeke. But there's a great question given the context of our college and those who are here in the room from an anonymous person online. How do we get the agricultural industry to contribute to carbon and global temperature reduction?
That is a great question. And it's a really tough one. We're probably not going to fully get rid of ruminants. We're probably not going to be able to convince everyone in the world to become vegan. And so I think that there's a lot of steps we can take around more intelligently using land, of producing more food in less space with less fossil fuel inputs, to open up more space for nature and for reforestation. I think there's also ways that we can encourage people to consume more of a plant-based diet, even if they might not be willing to fully go all the way. And I think that oddly enough, there is a role for technology in that too. I personally have stopped eating beef in large part because I really like Impossible meat. And so I just replaced it in all my recipes, and that has, 90% less greenhouse gas emissions associated with it. And so the fact that I can eat something that tastes like a hamburger that isn't beef and not contributing to the carbon makes it a lot less likely that I'll personally eat hamburgers. And so, certainly there is going to be a big role for, people making more ethical decisions around their food input. But also I think there's a role of technology, both in terms of alternative proteins and eventually perhaps even cultured meats to figure out ways to have much lower carbon, particularly beef. Other things, the benefits are a little bit more ambiguous. But there's also steps we can take potentially to reduce methane through feed additives that a lot of people are exploring, and other measures as well. Though there is an interesting debate about potential trade-offs between animal welfare and greenhouse gas emissions, because particularly for ruminants, the main determinant of their life cycle methane impacts is how long they stay alive. And obviously there's a trade-off if you're trying to very rapidly fatten up and consume cows. And so again, it's one of these thorny problems where we need better solutions than we have today.